Okay, let's do one more. This time, calculate the number of water molecules produced in 128 grams of O2. This is the only piece of given data, so that's obviously going to be the starting point. Let's start putting that out in our map here. The 128 goes above the O2. And my box, where does that go? Well, I know in my mind's eye that I have a mole quantity that goes there and a mole quantity that goes there. So I'm going to have to put it below this in the normal configuration where number of particles goes below the moles, right? Okay, so here we go. Let's take a look at that and let's work through it. I'm going to go from, this is where my box is going to be. That is the moles of what, that is the number of water molecules. So my flight path, what's it going to be? Pretty straightforward. I'm going to go from grams of O2 to moles of O2. And from moles of O2 to moles of water. And from moles of water to number of water molecules. What conversion factor do I need to get through this loop here on that path? I need atomic mass, and I get it from the periodic chart. How about this? I need the ratio of the coefficients using the balanced chemical equation. And how about going from moles to number of particles? I need Avogadro's number. How that looks on the, once we set it up with dimensional analysis, now that you know that, you take your flight path and follow that and set up your dimensional analysis equation. You're starting at 128 grams of oxygen. You're going to go from grams of oxygen to moles of oxygen, from moles of oxygen to moles of water, and from moles of water to molecules of water. And there you have it. Once you take your flight path, you can do a quick check to make sure that you grams crosses off, moles crosses off, moles of water crosses off. The only unit you have left is molecules of water. You're looking for molecules of water. Everything is perfect. At this point, you pick up your calculator, and what I did was 128 divided by 32 times 2 times 6.02 to the 10 to the 23rd means I have a total of 4.82 times 10 to the 24th molecules. That is approximately the correct answer. It's often sig figs because this is a typo right here, and that should have been 32.0. And now that answer is exactly right. If I left that at 32, of course, as an aside, that's only got 2 sig figs, so I would have had to just report 4.8. And that's it for this question. Let's switch it up and use a different equation this time. How many grams of magnesium oxide, that's what I'm looking for, put it in the gram slot, can be formed from the combustion of 42.2 grams of magnesium? It's going to be a pretty easy, now that we're getting the hang of it, we can easily see our flight path. We're going to go from grams of magnesium to moles of magnesium to moles of mag oxide to grams of mag oxide, using the periodic chart to find out these values and use your coefficients in the balanced chemical equation to work that conversion factor. Realizing that you have 1 conversion factor, 2 conversion factors, 3 conversion factors to get to your answer. To see what that looks like, let's do the flight path. Starting out with 42.2 grams of magnesium. I'm going to go from grams of magnesium to moles of magnesium. That conversion factor is, there's 24.3 grams per mole per periodic chart. And then for every 2 moles of magnesium, there's 2 moles of magnesium oxide. These are the coefficients in your balanced chemical equation. And then finally, I'm going to go from moles of magnesium oxide to grams. The atomic mass of magnesium, or the molar mass of magnesium, is 40.3. That is the weight of 1 magnesium plus the weight of 1 oxygen. If you pull those out on the periodic chart and sum them up, you will get 40.3. Multiplying that out, 42.2 divide by 24 times 2 divide by 2 times 40.3 will give you 70.0 grams of magnesium oxide. Now this problem, I want you to keep this in mind because when we go to the next video, we are going to use this very equation and this very calculation as the starting point for studying a concept called percent yield.